We're going to summarize a couple of important results and interpretations of Green's theorem. The first being, of course, our integral over c of f dot ds can be expressed as the integral over c of f dot t, and these are closed curves. Let's go ahead and close up this one. I think I've got the rest of them. Okay. The integral of f dot ds is then the integral of f dot dt ds, and over a closed curve, that becomes the integral of m dx plus n dy, and that is, of course, equal to the integral of negative my plus nx dA. The curl of f. Curl of f is partial with respect to x of I plus partial with respect to y of j crossed with mi plus nj, which we can easily verify, and we have done so in previous discussions, that this curl, this cross product, is equal to negative my plus nx times k. By now, you're going to recognize this as the integrand on the right-hand side of Green's theorem, and I think I pointed to the wrong expression here. Anyhow, that it follows then that this integral of m dx plus n dy being equal to the integral of negative my plus nx dA, this integral is just the integral of f dot ds or f dot t ds, left-hand side. The right-hand side is just the integral over r of negative my plus nx dA, but that's just the curl of f, which is negative my plus nxk, dotted with k. When we dot k with k, of course, we get 1, so the curl of f dotted with k is equal to this. So we have the statement, the closed integral, the integral over a closed curve, and I did miss one, integral over a closed curve of f dot ds is equal to the integral over the closed curve of f dot t ds, and that's equal to the integral over the region of the curl of f dot k with respect to area. And this makes a certain intuitive sense if we have a region where the vector field circulates in the direction around the curve, then the integral of f dot t around the curve, the vector is going to be close to the direction of the tangent vector, so this is always going to be a positive quantity, so we're going to accumulate a positive integral as we go around the curve. And when we have this kind of circulation, well, if that circulation continues, if we have circulation about some point within this region, then that circulation is going to imply that the curl integrated over the region is going to be non-zero. The curl being a measure of rotation. And if we have a bunch of little rotations within the region, all going in the same direction, then we're going to have a curl, a net curl, to integrate over the region, and that's again going to give us a result that's consistent with the interpretation of the integral around the curve and the integral of the curl over the region. Now we're leading up to some three-dimensional interpretations that involve divergence and curl, so we just want to complete this summary by stating the result that we proved in the preceding clip, that the integral of the normal component of our vector field around a curve, around a closed curve, is equal to the integral over the interior of the curve of the divergence of f with respect to a. So we have a couple of results here that are related to integrals of curl of f or divergence of f with respect to area, and these are related to either the normal or the tangential component of the vector field in a way that will become even clearer as we extend into the divergence theorem and Stokes' theorem.